Ladies and gentlemen, my name is Robert Riedel and I am CEO of Class 5 Photonics. My today's presentation is about our high-power optical parametric chirp pulse amplifiers at 1.45 to 2.4 micrometers mid-infrared wavelengths. In my talk, I will present two different high-power OPCPAs in the mid-IR. First of all, a tunable system with a wavelength range from 1.4 to 3 micron, an output power of about 10 watts and a pulse duration narrowband operation of 200 femtoseconds. The second system is a millijoule class 2 micrometer OPCPA with a central wavelength of 2 micrometers, an output power of 50 watts compressed and a pulse duration of 38 femtoseconds. But before I go into the details of the two systems, I would like to present you an overview about a selection of mid-infrared high-power OPCPAs that have been realized so far. So here we see repetition rate versus pulse energy, and we see that there are some quite energetic systems, for example based on KTA at low rep rate, and then there are some systems at higher rep rate here between 10 and 100 kilohertz. And you also see the diagonal lines. Those refer to the respective average power. So here, for instance, at 100 kilohertz, 100 microjoules, we have about 10 watts of average power, and most systems have been realized now here between, let's say, 10, 20, 30, 40 watts of average power in the mid-IR. So this is due to the availability of pump lasers. Most pump lasers in the picosecond range are delivering power levels between 100 and 300 watts, maybe up to 500 watts. And so this explains the results, like building this, this cloud of systems in this range here. So the first system I'm going to present is a system based on KTA with about 60 microjoules of output energy at 167 kilohertz. And the other system is here a broadband system at 1 millijoule, 50 kilohertz. And this class of systems really needs very powerful pump lasers above 500 watts. So we are talking about the kilowatt class of picosecond ytterbium YAG lasers. And we could already demonstrate successfully in cooperation with SLAC based on KTA the MIR operation here at 1 millijoule at 100 kilohertz, so 100 watt output power at 1.75 micron and about 65 watts at 2 micron wavelength. So now this here is a 50 watt system compressed at 1 millijoule, 50 kilohertz. Okay, so let's start with the tunable mid-infrared OPCPA. We call it the white dwarf HE. HE stands for high energy. Because we also have a high rep rate system that is not covered here. This will be presented in the next presentation. The schematic is always very similar. We have one pump laser, which is quite compact, and one OPCPA. So the total footprint is about 2 times 1 meters, roundabout. And now for this particular work, we have used a 100 watt ytterbium fiber laser. So this box is just representative. The fiber laser is a bit different. I will show you a picture later. But the OPCPA, the white dwarf, always looks basically like this. So it's a quite compact package here, given the 10 watts of output power. So let's have a look on the schematic of the system. The pump laser is an active fiber systems ytterbium fiber laser. So it has a 1 micron central wavelength, 600 microjoules pulse energy, which is quite remarkable for a single fiber laser, 167 kilohertz repetition rate, 200 femtoseconds, and correspondingly 100 watt of average power. So we take all this power of 600 microjoules in the white dwarf box, and then we split the beam. First of all, we need a mid-infrared seed between 1.4 and 2.1 micron. So the way to do this is to produce a broadband white light in a bulk YAG crystal, and we are interested in the spectral range between 680 and 815 nanometers. Now, the design aspect was to produce Fourier limited 200 femtosecond pulses. So the idea is to use temporal filtering, which means we stretch the seed pulses temporarily so that only the spectral content corresponding to 200 femtoseconds Fourier limit will fit the pulse duration of the pump, which is 200 femtoseconds. This we send into a difference frequency generation stage that is pumped collinearly with a second harmonic, so here at 550 nanometers. And as a result, we will get narrowband tunable pulses between 1.4 and 2.1 micron. So this is now being used as a seed for the main OPCPA. So as you can see, the main OPCPA is now pumped by the remaining 460 microjoules of the pump laser and amplifies the signal range between 1.4 and 2.1 micron and the idler range between 2.1 and 3 micron wavelengths. And those two ranges here are separated by a dichroic beam splitter, so transmitting the shorter wavelengths and reflecting the longer wavelengths here. So as you can see, we have two outputs and the whole system is basically tunable through the a long range. In addition to that, there's a variable beam splitter that can send out the fundamental beam, which is at 1 micron, 200 femtoseconds, and that can also be used for experiments or even for driving further optical parametric amplifier stages. So let's have a look on the key results for that system. Here we see spectra of the tunability in the mid-infrared from 1.4 to 2 micron. We see the narrowband spectra that correspond to roughly 200 femtoseconds. And in gray, here you see the pulse energy. So we are using KTA as an amplifier crystal, type 2 phase matching. The phase matching limit is slightly below 1.4 micron, and this reflects also in the low conversion efficiency. But here at 1.5, 1.55 micron, we get the highest efficiency above 60 microjoules. And then we remain more or less constant over the whole range up to 2 micron. And then on the other side, the idler region would start, which has not been measured here with this infrared spectrometer. So we have the signal output that corresponds to 10 watts of average power here at 60 micron, 167 kilohertz, and pulse duration 200 femtoseconds. And as promised before, here's a picture of the system right after the installation in the lab. In the background, we see the active fiber systems pump laser. This is a 600 microjoule fiber amplifier. Here we have a separate grating compressor, and then we have an incoupling section into our white dwarf OPCPA. It's an 80 by 80 centimeter box. It's temperature stabilized, and here in the front you see the three outputs: signal, idler, and the 1 micron fundamental from the pump laser. And now in the second part of my talk, I would like to talk about a different beast. This is a millijoule class 2 micrometer OPCPA. You see we have a kilowatt picosecond pump laser, which is an Amphos InnoSlab system. There is a first box, which is a 400 watt preamplifier. Then there is a kilowatt system in the second box and a big grating compressor in the third box that is sent into our supernova OPCPA. The dimensions here are 80 centimeters by 120 centimeters of the supernova OPCPA. So it's actually as compact as a white dwarf HE. So let's have a look on the schematic of the system. We are starting here with an Amphos pump laser. It's an ytterbium YAG InnoSlab, a multi-stage system, 1 micron wavelengths, 20 millijoule pulse energy, 50 kilohertz, 1.2 picoseconds. So it's about a kilowatt. The main exit has a big grating compressor giving 15.2 millijoules, which corresponds to 760 watts of average power. That is being used to drive basically the main OPCPA stages. And then there's also an auxiliary output that can be operated independently of the kilowatt output with an on compressor of about 1 picoseconds, and that gives us about 30 microjoules at 50 kilohertz. So this auxiliary output is being used to drive basically an independent DFG seeder that is a difference frequency generation stage plus a two-stage OPCPA to generate a broadband seed at 2 micron. This is being used for the first OPCPA stage. It is pumped by about 600 microjoules from the main pump. then stretched in the bulk stretcher, and sent into the two OPCPA main stages that give a final compression and output after the compressor of about 1 millijoule at 50 kilohertz, which is 50 watts. So in terms of dispersion management, we have a positive chirp coming from here, and of course most glasses used here are negative. So we use a bulk silicon stretcher to kind of counteract this negative beamline chirp here. And then finally, we have negatively chirped mirrors. Another important aspect is, as these two outputs here are independent, they are from the same oscillator, but the beam path and the thermal properties are totally different. So there's a slow drift to be expected between the seed and the pump. So we have to measure both arms in an optical cross correlator and then to send it through a delay stage to stabilize the timing between signal and pump in this high power OPCPA system. So here are the data that we could produce. This is the DFG CEDAR output. You see we are amplifying between about 1.85 to 2.3 micron. We have a nice beam profile here with an infrared camera. The main output basically maintains the bandwidth. We have 1.9 to 2.3 micron spectral bandwidth here at a pulse energy of 1.4 millijoules. So this is being amplified with an average power of 70 watts, and in the inset we also show you the amplified beam profile. In terms of stability, this is an example that has been recorded. This is about 12 hours of average power. So we are operating here at 2 micron, 1.4 millijoules, 70 watts. The standard deviation is 1.44 watts. That corresponds to a 2% standard deviation here of this power output. Finally, the temporal characteristics have been characterized using frequency-resolved optical gating. So these are frog measurements. You see the measured trace and the reconstructed trace. And then in the time domain, we get a very nice pulse. So this whole system is based on a passive dispersion management. There is no active phase shaper involved. It's just bulk materials and chirp mirrors, which puts a high demand on the fabrication quality of the dispersive optics in this system. But as you can see, we were able to reach a pulse duration of 37.7 femtoseconds at the energy of 1.1 millijoules. So the average power out of the system is 55 watts. And these are our colleagues installing the system in Amsterdam. We really have to say that it has been a big effort between Christmas and recently under Corona restrictions to get this system happening from the Amsterdam side and also from the Class 5 side, to get all the travel exemptions organized. And then now you see the colleagues are working with masks under extreme power conditions, and they had to do COVID tests entering the country, exiting the country, and had to stay in quarantine after each travel. So it was really a big effort and a very successful effort that we are all very happy on. And we are really happy to present you these very recent data here. So with that, let me summarize this talk. I presented you a tunable mid-infrared OPCPA first, with a wavelength range between 1.4 and 2 micron in the signal, and then 2 micron to 3 micron in the idler at a pulse duration of 200 femtoseconds, a pulse energy of around 60 microjoules, output power of 10 watts, and a rep rate of 167 kilohertz based on a fiber pump. And in the second part, I presented a millijoule class 2 micrometer OPCPA at 2 micron wavelengths broadband, with a pulse duration of 37.7 femtoseconds and a pulse energy of 1.1 millijoule. So with an average power of 55 watts and a stable operation over many hours, this is an ideal system to drive the next generation soft X-ray and attosecond experiments. With this technical summary, I would like to thank you for your attention, and I would like to look forward to the next presentation.